Despite all the advances in the space industry, access to space still remains very expensive. There are a wide variety of different vehicle architectures which allow a rocket to get to space. Historically, electric pump has been ruled out due to the low power density of batteries. However, recently, batteries have become much more power dense, enabling architectures such as electric pump. An electric pump architecture is very well suited for a mid-sized launcher, something to deliver satellites, small satellites to orbit, but not tons and tons and tons to orbit. The electric pump is brilliant because it's incredibly simple to develop compared to a turbo pump, while still offering pretty high system level efficiency.
The inspiration for this project came for the Yellow Jacket Space Program, a club some of us are part of on campus, which is aiming to be the first college team to send a liquid-fueled rocket to space. They're currently developing a pump, and we got the specifications, the functional specifications from them on how to design our electrical system to support that. And the rest of the functional specifications came from just like doing research online and system analysis to determine, say, like what the switching frequency or input voltage should be for our system. And then we kind of developed the system from that, which you can see here, which has a battery pack, high voltage management board, an inverter, and a motor, and then of course the pump at the end. For the purposes of senior design, we did not do the battery pack because that'd be too complicated of a project to do with the time we had. The high voltage management board basically is responsible for that interaction between the battery pack and the inverter, ensuring that there is safe and proper distribution of power from the battery pack to the inverter, ensuring that the inverter capacitance, which is very large, is pre-charged so that there's no overcurrent event or anything that would make the system unsafe, as well as including safety measures so that we can stop the test or stop the system in the event that something is going wrong with like a hard button, a hard like e-stop or something like that.
Now going into our inverter block, the main purpose of our inverter is to convert the DC voltage produced by a battery pack and turn it into a usable AC voltage for our motor. Now, inside of our inverter houses a microcontroller, and that microcontroller has a field-oriented control algorithm that's used to control the speed of our motor. Now, it does this by sending gate signals to our FETs and controlling the rate at which they turn on and off. Now, another purpose of our microcontroller is to monitor our system's health. That includes monitoring the temperature, the voltages, and currents through our systems, and making sure they're within a stable and safe level. Going into our experimental results, our main loss mechanism is going to be our MOSFETs, in which case we have 6 of them. Looking over our graph of output power and efficiency, we notice that at low output power, we have very low efficiency. However, going up to our operating power of 3 kilowatts, we notice that we have an efficiency of 96 to 97%. Going over to our commandability of our inverter, we notice that if our user inserts a certain commanded rotor speed, we have around 0.15% of error in our measured speed using a tachometer. And this is all due to the field-oriented control implemented by the Kaminsky microcontroller.
Field-oriented control is a control strategy in which the rotor and stator magnetic fields are aligned at 90 degrees offset to maximize torque. Normally, field-oriented control is run with closed-loop feedback, in which a position sensor is used to estimate the position of the rotor flux, and the stator currents are driven by a series of cascaded PID loops to ensure that the stator flux leads by 90 degrees. In our case, we chose to eliminate the use of a position sensor by running the algorithm open loop and generating a rotating magnetic field of the stator that rotates at the synchronous speed that we want. And using the strategy, we were able to command the motor to various speeds with smooth ramp up and ramp down.
Thank you very much for watching our video, and we look forward to seeing you tomorrow at the Senior Design Expo.